Welcome. In this video, we're going to discuss some examples that build upon what we talked about in the previous video. So let's start with the first example. Example 5, it says, find a mod 12 trick and then find the remainder when we divide this number by 12. In the previous video, we discussed some methods for finding mod magic tricks, as we call them. Quick ways to reduce numbers in various different mods. There was two methods that were introduced. One was talking about trying to discover a nice power of 10 in your particular mod, and the other was taking two mod tricks that you already know about and combining them to make another one. Let's try to use that second method here. So because we have mod 12, we want to think about two numbers that multiply together to give us 12. So you might say, okay, 2 times 6 gives me 12. So those two numbers multiply together to give you 12. But in the previous video, we also discussed that when you pick your two numbers that multiply, you need to pick them so that there's no common factors. So the GCD of the two numbers here, 2 and 6, needs to be 1. But here it's not 1, it's 2. So we can't pick these numbers. However, we could pick 3 times 4 is 12. Because 3 and 4 have no common factors other than 1, so the greatest common factor is 1. So now we know that we can combine the trick for 3 and the trick for 4 to give us a new trick for 12. So how does this work? We can take our number. In the previous video, if we call this number n, we have shown that that number is 0 in mod 3. And we also could take a look at that number and notice that, okay, in mod 4, we just have to look at the last digit, which is 6, and 6 is congruent to 2 in mod 4. Okay, so we have a number 0 in mod 3, and that very same number is 2 in mod 4. How do we figure out what that number is in mod 12? Let's think about our number. Our number is n, and let's think about what might happen if you divided that number by 12. So if we chop this up into 12s, so we have some multiple of 12, so I'll write m multiplied by 12, plus some remainder. Now let's use this first part that we know this particular number is 0 in mod 3, or it's a multiple of 3 is another way to say that. So our number could be also viewed as 3 times 4 multiplied by that number m. I just broke the 12 up into 3 times 4, and we'll carry the plus r from the previous step. Now, if we consider our number in mod 3, so I'm going to take what I just wrote and break it up into mod 3. This first part, the first term here, becomes 0 because 3 is the same as 0 in mod 3. So we would get 0 times 4m plus r, or simply just r in mod 3. So we know that our number that we are trying to investigate here, this number n, in mod 3 is the remainder when we divide by 12, and it's 0 in mod 3. So what are the possible values of that remainder? Let's think about this number r. So r is a remainder after dividing by 12. So that r could be either 0 or 1 or 2 or anything all the way up to 11. But we also know more about r. We found that n and r, through this chain of equality and congruence, r is the same as n in mod 3. So taking out my green pen, we'll explore another route on what we know about r. r is the same as n in mod 3, and we know that n is 0 in mod 3, so therefore r is also 0 in mod 3. So which possible choices could we have for the value of r? Well, all of these numbers that are 0 in mod 3. So that could be 0, or it could be 3, or it could be 6, or it could be 9. Those are the possibilities. This pattern is quite easy to notice if you just add 3 to the remainder that you start with. Okay, so let's do something similar for mod 4. So my n value is either 2 in mod 12 or 2 plus 4, adding the mod. It could be 6 in mod 12 or it could be 10. Those are all the possibilities. So now after we're done this process, we just need to look for the match. The one that matches in the two lists is 6. So 6 is the remainder that we've been looking for all this time. All right, so in the next problem, we are going to use the other method that was discussed in the previous video to try to find a trick for 7. And we'll use that trick on the same number again. So the other idea that we had was to take powers of 10. So we'll write 10 to the power 1 and reduce that in mod 7. So we would get 3. And we'll keep going until we either get 1, 0, or minus 1. So 10 to the power 2 would be 10 times 3, which is 30. And if we reduce that in mod 7, maybe we'll subtract 28 to get 2. So 10 to the power 3 would be 2 times 10, which is 20. And then from 20, we can subtract 21 to get minus 1. So we're happy about getting the minus 1. We can stop this process here and move forward with 10 to the power 3 as our nice power that reduces in mod 7. Okay, so to describe this trick in general, let's just write down an arbitrary number. Let's just say we have an 8-digit number, for example. We have A, B, C, D, E, F, G, H. So for this number, because we got 10 to the power 3 as our nice power that reduced to minus 1, I would like to see 10 to the power 3 in this number that I just wrote down. So break it up into groups of 3. The F, G, H will be my first group. And then my next group of 3 will be C, D, E. So C, D, E would get multiplied by 10 to the power 3. And then the final group is just AB. There's just 2 digits there, but that's fine. So AB would be multiplied by 10 to the power 6, or you could write that as 10 to the power 3, all raised to the power of 2. So when we do this, each power of 3 for 10 changes into minus 1 because we're working in mod 7. So AB is multiplied by minus 1 squared plus CDE is multiplied by minus 1 plus FGH. So as a result, what we can do is alternately add and subtract groups of 3, starting with adding from the right-hand side. And notice that this -1 that we just wrote can be changed into minus CDE instead of plus and multiplying by -1. Okay, so let's put our example to the test and try to deal with an actual number. So my number is 2007, 1986, and I want to take that number, separate it into groups of 3. So 9, 8, 6 is my first group. I want to add that first group. And then my next group is 0, 7, 1, or just 71. So I'd like to subtract that group. And then the final group is 2, 0, so I'm going to add 20. So my quick reduction in mod 7 is made, and now I just need to reduce this number. All right, so to do the reduction, I'm just going to think of numbers that are relatively easy to work with. 20 minus 71 is minus 51. And then from the 986, I'm just going to think, let's just take away 700, something straightforward. So that would give me plus 286. And then from there, maybe from the 286, how about 28 is 7 times 4. So 28 times 10 is also a multiple of 7, so we could subtract away that. And then from the 51, how about we take away 49? And this would give us minus 2. 51 changes into 2. And the 286 changes into 6. So as our final result, we get 4 in mod 7. And this method that we just used, I think that's a lot quicker than long division. Once you know about this method, of course. I mean, maybe the whole problem did take us some time to figure out the trick, but now we can continually use this trick over and over and over every time we want to divide things by 7. All right, so if we scroll down from here, on the next page, we have a nice summary of the first 12 mod tricks. So for mod 1, the remainder is always 0. There's never a remainder. For mod 2, it's either even or odd, and to decide, you can just look at the last digit and reduce that in mod 2. In mod 3, we talked about adding up the sum of all the digits and then reducing that in mod 3 to find the remainder. And the reason why that trick worked out is because there was a nice power of 10, really just 10 to the power 1, and that 1 gave us groups of 1, so each of the digits gets separated out. In mod 4, we found that 10 to the power 2 was 0. So from there, we can just look at the last 2 digits. In mod 5, you can just look at the very last digit. The reason why would be that 10 to the power 1 is 0 in mod 5. In mod 6, we discussed using 2 tricks from before to give us a new trick. So we used the trick for 2 and the trick for 3 to combine to get a trick for mod 6. Mod 7, that's the one we just did in this video. Because it was 10 to the power 3 that reduced nicely, we did groups of 3. And because 10 to the power 3 reduced into -1, we had to do that thing where we alternately add and subtract those groups. In mod 8, it turns out that 10 to the power 3 is 0. So you would look at the last 3 digits. In mod 9, 10 to the power 1, just 10, reduces nicely to 1. So we add up all of the digits separately, groups of just size 1. In mod 10, 10 itself reduces to 0. So you just look at the very last digit. In mod 11, in the previous video we talked about that one, 10 to the power 1 is minus 1 in mod 11. So that's where the alternately adding and subtracting the groups comes from, because we got minus 1 as our nice power of 10, and it was 10 to the power 1, so we just have groups of 1, alternately add and subtract all of the digits. In mod 12, we discussed that earlier on in this particular video. We use the trick for 3 and 4 to combine to give us 12. Let's do some more examples on the next page. Okay, so the first one says find a mod 21 trick. So we need to think of two numbers that multiply together to give us 21. So 7 times 3 is 21. And then we need to verify that those two numbers that we picked have a greatest common factor of 1. So 7 and 3 indeed have no common factors other than 1, so 1 is the greatest. So the number, this number that we keep working with, we'll just call it n for convenience again. In mod 3, we discovered earlier that that number is 0. So my number in mod 21 only has so many options. My number could also be 0 in mod 21, or it could be anything that we'd add 3 to. So it could be 0, or 3, or 6, or 9, or 12, or 15, or 18, and we can stop there. We don't have to go beyond 18. The next number that you would get in this pattern is 21, but 21 is never a remainder. The remainder is from 0 all the way up to 20. Okay, and n in mod 7, as we discussed in the previous problem, was 4. So what does that mean? For mod 21, our n value, it could be 4, or it could be 4 plus 7, so 11, or it could be plus 11 again, so 18. Those are all the new possibilities for our remainder in mod 21. So what we have to do is look for the match in both of these lists, and our matching number is 18. If we've done this correctly, there will always only be one matching number in the two lists. If you find two numbers that match up here and those two numbers match down here, something has gone wrong in our process. There should be just one match. Okay, let's try the next problem. So in this problem, we have a mod 33 trick to try to deal with. So we'll try to think of two numbers that multiply to get 33. So we could do 3 times 11 equals 33. And those numbers also have no common factors. So previously, we found that n in mod 3 and 11 are both 0. So that tells us right away that the matching in the lists that we would write down for mod 33 is 0. The one match that we would get is 0. So we don't even really need to write out the two lists because we have the result right in front of us. N is congruent to 0 in mod 33. Okay, we'll do one more example for this video where we'll discuss trying to find a mod 37 trick. So this will give us an example of the other method, trying to find a power of 10 that reduces nicely. So if we do 10 to the power 1, we get just 10 in mod 37. 10 to the power of 2, that would be 100, and that would reduce to 26 in mod 37. And now 10 to the power of 3 would be 26 times 10, So 260, and that reduces to 1 in mod 37. So we're happy to stop here. And 10 to the power 3 is our nice power. So this means that if we took an arbitrary, let's say 11-digit number, for example, let's say it's A, B, C, D, E, F, G, H, I, J, K, and we wanted to reduce that nicely in mod 37, we would break that number up into groups of 3. The first group wouldn't be a complete group, but that's okay. And the next group would be C, D, E, and then F, G, H, and then I, J, K. And because we got 1, we would add all of these groups together. So plus, plus, plus. Okay, so now let's try to take our number 2007, 1986. If you're wondering why I picked that number, there are years that are very important to me. 1986 is my birth year, and 2007 is the year that I first became a mathematician and got to lecture my first class. So I want to take this number and break it up into groups of size 3. So 9, 8, 6. And then the next group is 0, 7, 1, so plus 71. And then the final group is 2, 0, so plus 20. So if we add this all together, we get 1,077. Yeah, so another nice tip that we could do is we could take this number and use that trick once again. So you could do groups of 3. So the first group would be 0, 7, 7, and the next group would be 1. So you could say that this is 1 plus 77. You get 78, and then from 78, we could subtract 37 twice. So 74 could be taken away from that, and then as a result, we would get 4 in mod 37. So the remainder of my big number, we found it pretty darn quickly here, is 4. Thanks so much for watching this video all the way to the very end. We'll see you on the next one.